Słychać mnie? O, świetnie. Hello, welcome to my presentation. It's good to be back at GeeCON. I hope you're having great time, like I do. This is second day, so you probably know the Slido.com tool. Use GeeCON 2019 code to join on the conversation. It's room number 11, in case you're lost. When I thought that Slido was a good idea, I put the QR code. It's on every slide, so you can join in late, just scan it and select room number 11. But it seems that this tool is something that it has high latency and low throughput. So if you start writing a question about the slide, probably I will see it on 5 slides later. And so if you want to just interrupt me, ask questions, or disagree with something I'm saying, maybe you should shout or raise your hand. Very helpful GeeCON staff will give you a microphone and we can talk bi-directionally. So to the presentation of performance. Who doesn't like performance, right? Who doesn't like optimizing his code, even if for the sake of the optimization itself, making it more beautiful, more clear and friendly to the machine. It's a dream job, right? Probably there is no manager that did that, but if one came to you and said, okay, you have 2 iterations now booked for making this your microservice code more elegant, right? Who would said no to this? Well, I don't know any developer who would said, okay, but you know, there's those user-facing features that we need to implement because users are waiting. Maybe no, let's not do that now. Let's do the architecture refactoring or code refactoring later. Said no developer ever, right? In this presentation, I will try to argue both sides. One side is for more customer focused or product focused, where this question and would be the right answer. This answer, let's do the user-facing features first, would be the right answer. I hope I will make a good case for this, and where this is the most important thing in a life cycle of a startup, product, or a company. Then we go on a trip through conferences and white papers to find out the point of this presentation. So to answer this question I'm posing now, and in the last part I will be talking about what I promised in the abstract. So about dark corners of the silicon that will allow us to implement actual optimizations and have this promised performance. A few words about me. I'm Tomasz. I worked many years at Codewise. Right now I still work there, but I'm heading a small startup within our company that focuses on monitoring and metrics for your apps and servers. My Twitter handle you have here, so you can tweet at me now or later after the conference. I will happily answer any of your questions. Or criticism. What is my position, or what was my position at Codewise? Well, I was a tech lead, and or some companies would call it engineering manager, and it happened like in many small companies when a company you're working for is no longer 10 people team, it's growing. It's natural that the initial developers with most of the business knowledge or the technology knowledge will become some kind of leads in this growing company. And usually they wouldn't know what to do with this new position. So I went and Googled what should I do and what I shouldn't do, and I found this interesting article, How to Fail as a New Engineering Manager in 8 Easy Steps. First step was keep coding. Well, so I kept coding, so I guess I'm the failed one. And when preparing this presentation, thinking about my history of the products that I implemented and maintained and optimized, there was this revelation that probably I spent half of my career optimizing allocations on a JVM, which frankly is very sad thing, and it made me rethink my life choices. Maybe I will visualize how I looked at that point. This lady, as you can see, she no longer wants to optimize GC on JVM, but probably she wants to go to Bieszczady. And obviously it's a stock photo. What's interesting is when where was it placed? It's a main page of a small conference called FADS. FAD is something that is overhyped, short-lived, without substance, and it's a short for failed aspirations in database systems. Don't look at the database part. It was just part of a database conference, but think about the premise of such mini conference. Like in GeeCON, let's think that we have one track, 3 days, of a mini conference when people go in and say about failed aspirations. The idea here is that you submit a paper or a presentation about the system you worked on or idea you worked on that seemed like a great one when you started and turned out to be a terrible failure in the end. So if we would like to repeat this conference, then I would like to make a small call for papers. Who would like to present something on this conference? Are you guys in sugar coma or you didn't work on any system at all? Okay, so we can imagine people from, for example, Korba camp coming and saying, look, we thought that having an objects accessible remotely via synchronous calls is a good idea and will make lives of everyone better. Or people thinking, okay, if we have services and connect them using XML calls, then that's a good idea, right? And it turns out that it wasn't. It's the same with using JSON to communicate microservices. I hope at some point author of this idea will present on such conference. I can keynote there. I really have some systems that turned out to be not something I'm proud of, because it's easy to bash some other people's systems, but I have some of my own. There was this system, at a startup, you live in a greenhouse. It's a place when it's, especially the startup that has a lot of clients, paying clients, you're profitable, everything's fine. So it's sunny, cozy, warm, and you don't want to go outside. At some point, someone will throw a brick into your greenhouse, or as in our case, you outgrown the greenhouse, you want to get out of it into a harsh, cold environment outside. So myself and a small team were tasked with creating the system when our internal client came in and said, we provide products to our clients to analyze data. They look at this data, analyze it all day, every day. Maybe we should do the analysis for them and sell this to them. Well, it seemed like a great idea, right? What can go wrong? Well, we took this data. It was hundreds of gigabytes per user. It's a relative term. Big data is a relative term. If you're Facebook, you can spin 10,000 servers and have this analyzed in minutes, right? If we can't do that, because no one will pay so much money for this, we had to be to optimize the code, to be performant. We learned a lot about JVM, about Linux kernel, how to handle it, so we can actually analyze all this data. It was a fun project. In the end, we showed it to the clients. and no one bought it. It just wasn't what they wanted, and we learned this a long time after this project should be scrapped. So we turned into some, and by we I mean actually myself, because as a company we had a lot of products that were close to the clients. This was something new. So we had already products working with clients. So this failure is just mine, not of those other products. And we turned as a company and as a team to some different ways to validate stuff instead of just diving into performance and writing great code. There is one book which is summarizes one of the approaches that is popular. Well, I don't know if it's popular. They say it's popular in Silicon Valley for startups. And the authors of this book, you see Sprint. It has nothing to do with Scrum. It's not that. The authors of this book work for Google Ventures. It's a company that invests into startups, and obviously they want the startups to succeed. So they gather the team, go to those startups, and help them validate the ideas that they develop. It doesn't have to be the core idea of the startup. Sometimes it's like a new web page or some pivot. They help startups like Slack to better define what they're doing. And the idea here is that you have 5 days to validate a product idea. You start, it's a 1 work week. You start on Monday by inviting clients for Friday to test the product. You have nothing usually. Sometimes you have something, but usually you have nothing at that point. You already ask clients to come on Friday. This can be some random people to test your web page, or maybe some oncologist if you're doing a tool for medical purposes. And you have 3 days when you invite subject matter experts, when you invite people who can influence the project, do the brainstorming, and analyze the problem and the solution so that you have something on Friday. On Thursday, you have 1 day to implement it. So you have 1 day, and actually those people say, you know what, don't implement it, just if you can get away with it, make a PowerPoint presentation. People will think they are clicking or something, and actually it's a PowerPoint presentation. So it's for some it can be getting back to the roots when we were at the university, and there was a deadline for some university project. It wasn't implemented, so we had to fake our way through. At that point, I thought it's cheating. Well, it's not. It's the startup way. So what's important here, and what I wanted you to take out from this, is that it takes only 1 day of fake implementation for them to validate a product idea. So what's the point of actually implementing anything at this stage? Maybe we can implement anything later, where it's also not advisable because it's just a first step in creating a successful product. Why would you optimize this cycle, this production pipeline so much? Well, everything costs. If you are a large company, you can bet on technologies that can fail, like Corba. Some companies, large companies, cannot afford failed projects because some VP will look bad, so the project will go on and on. And some, most companies can't afford the failed projects because of money they put into such project and cost of lost opportunities of creating something else. Well, getting back to costs, this is from some blog post on no fluff jobs. It's a nice job board when all the job advertisements need to contain salary ranges. And this is old. It's like 2 years old. It says that top range for senior developer is 17,000 zloty. Probably right now is 22. I don't know. It's a lot. For the purpose of this presentation, let's assume that with cost from the side of the employer, it's about 10,000 a month. Okay, so this is good, right, for us. We like this because this means we get more money, but this money must be spent wisely. You might say, okay, but if we do a crap of a job, then it will be slow, it will won't work. Well, obviously it has to work somehow to gather to get the clients use it, but slow, where if it's slow, just put it on a bigger server. This is an example of a largest server that Amazon has. It has 128 cores, 2 terabytes of RAM, 2 terabytes of very fast NVMe SSD, and it costs 20,000 a month. If you reserve it, you can go to almost 10,000. So the question here would be, should we spend engineering time or just add another server like this? If you think that this server is not big enough, it's an old one, I think next year there will be something bigger. This is a fun fact, comparison of IBM ASCII-White, which is a supercomputer installed in the year 2000, and NVIDIA Volta 100 GPU from 2 years ago. And well, it's a glorified gaming rig used for data center. The double precision performance number of teraflops is the same here. The only difference is that the supercomputer weighs 100 tons and the graphic card weighs half a kilogram and needs 300 watts instead of 3 megawatts to work. So this is the progress that we have in 17 years. You might have heard this quote when I don't know who said that the staggering improvement in hardware is constantly cancelled by the software industry that makes bigger and more bloated software, and this cancels out, right? So maybe that's why we have this progress here. And but as I'm a developer, and I guess you feel the same, even if we agree that this course of action makes sense for the companies, it still seems a little wrong. Here we have from a picture from the internet. You have a Chrome browser with 2 tabs. One tab has Gmail opened. Second tab has Windows 2000 running in the browser with Internet Explorer inside. And guess which tab consumes more resources, right? So there is something wrong with all this. It's a little like from Philip Dick's The Man in High Castle. We're in this reality. It probably makes sense, but there is something subtle wrong with it still. To finish this part, I would like to make a summary of a developer that would probably find herself or himself in this environment, and this is he would have qualities that I admire very much, and sometimes I do wear this hat. So it's 0.1x developer. You might have heard about 10 times developer. Like the difference between junior developer and senior one who has all the knowledge and experience is 10 times probably in how fast they can develop stuff. I like the 0.1 developer. There are links on the bottom to some people that described this for me before. This kind of developer, when on the project, he would say, okay, maybe not add this, let's not add this feature now. Maybe we don't need it. Maybe we shouldn't adopt this new technology, or maybe we shouldn't automate it yet. Just do it manually and go on with the project. There's some quotes from a guy that I guess works more on hardware, so he would say, can we approximate the result and no one will notice? So actually we don't have to do it real, or can we use a small lookup table? This is the set of questions to be asked. But like I said, there's something wrong with this approach, and we wanted to find out what and how we can have any other approach. So me and my team went to, we started with a conference called Very Large Databases Conference, and it was in Munich, so there was a lot of fun to be had. 1 year later it was in Brazil, so maybe the timing wasn't that good for us. And this conference is really interesting one. If you're a strange person that likes to read papers, I salute you. And most of the papers about data processing would be published on this conference. And there you can meet a lot of people, not only from academia, but also vendors of databases, data processing systems like Snowflake, Oracle, SAP HANA, people from Intel, NVIDIA talking about their roadmaps, a lot of interesting stuff. And there was a keynote. As all good keynotes, it was controversial. And but not only was it funny, but it also brought some deep insights into the about the industry. So the author of the keynote said, "Okay, we are the database community. We're processing data. Let's say we take any company in the world, maybe apart from Google and Facebook or Large Hadron Collider. We take the data of this company and we can find a data processing system that we take this data and answer query on this data, any query, in 150 milliseconds. It was like a few years ago. Let's say there's a progress in software hardware, so this we can answer this query next year in 80 milliseconds. Then 20. What's the problem here? Well, the human perception is about 200 milliseconds. So the conclusion of this keynote was actually, well, what's the point of us being here at all? We already got everything we can. There's no point in making it faster, right? Obviously, there were some bright sides. They say that big data is the lifesaver. There was a picture of a drowning man getting the life vest called big data, because that's the lifesaver for big data for big database vendors. But the point stands, and as you can guess, that's not what we were looking for there. So we dug deeper, and we found an interesting publication from 2011. You might notice that I will be going back in time. The last publication will be from 1970s, I guess. So that's the best time to have really powerful insights from about computer science. It's the papers from 70s and 80s. In this paper here, authors took some industry standard benchmark, so for databases. So it's like a set of data and a few queries. They took one query from it and ran it against databases available back there. There was database X, it's probably Oracle, but it was labeled X. It took 28 milliseconds to process this given query. MySQL at that point 4.1 was 27 seconds. MonetDB, which was a cutting-edge analytical columnar data store, fair enough, it was quite faster, 3.7 milliseconds. And last thing they did is implemented a simple program in C that implemented the logic of this query. So no parsing, no query plans, just a small program that does one thing. So it was probably a first microservice, and it was 220 milliseconds to process all this data. So if we have a developer that decides to actually optimize stuff this way, when we have a multi-million-dollar database or running probably on custom hardware versus a hand-coded C program, well, it's more like 100 times developer, right? And in terms of cost, even more. Even if you don't know C or don't know anyone who knows C, this seems like a good approach to try. The second paper that is relevant here, even more so, as on this conference I've seen several talks about streaming systems. The talks were very nice. The systems, well, the authors of those of this paper have some different ideas about those systems, and what they did is they took several papers, other papers, that described some research on a scalable system. Of course, the authors of those systems said it's a state of the art. So we have some data, we have some algorithm, it is implemented in this scalable system on many nodes, running in this time. It's a state of the art result. And here's a summary. So these are systems described in several white papers. There's a number of cores that were involved in producing the computation. What's nice is that all those systems use the same data set. It was some social media data set, connection graph between people, and they run some graph algorithm on them. The algorithm, the result was the same. Algorithm was implemented differently by those different systems. You can see that there were systems with 16 cores or 128. These were distributed, so not on one machine. We can see Spark is the slowest one, obviously. The fastest one seems like the one that runs 200 seconds. And the author of the paper that I'm describing, Frank McSherry and friends, they wrote something like this. Okay, so now we are going to introduce some new candidates for the state of the art, which is running a for loop on my laptop. And sure enough, how do you think the result compared to these systems? So every time you see a Spark cluster or Kafka cluster, some streaming computation running on Amazon or some other cloud service running on many nodes, just think about it, how fast it would be running on your laptop. So it was the fastest system compared to all those others. And what they defined is the cost in the name of the paper is short for configuration that outperforms single thread. So this is a metric for some system saying, okay, how many servers you need to put there to have it run faster than a competent implementation on a laptop. And what's interesting, there were follow-ups to this paper on his blog, and what's interesting, some of those systems had infinite cost. So there was no configuration that would run faster than a single thread. Okay, but as we know, when Apollo 13 said, Houston, we have a problem, Houston should have said, negative, Apollo, there are no problems, only opportunities. All right, so this is an opportunity for us to optimize. So what's okay, there's a question. Scalability is not only about performance. How would you comment on this? The scalability, sure, it's that's why the authors of the paper say about cost of the scalable system. So the system is scalable. It means you can add more and more servers and it computes somehow faster or be able to contain more data, but you pay a cost in coordination of the servers, and this cost is offsets what you get from the fact that it's scalable. And if you say that, okay, but if there's data set that is too large for my laptop, well, obviously there are such data sets, but you can still run a server with one thread on this instance from Amazon. There was this interesting page, it was called "It Will Fit in RAM." it's no longer live. When you go there and you put into a edit box how much data do you have, and it will find you a server on Amazon or some other vendor that will contain this in RAM. And if it couldn't, it would say, don't worry, it will fit in RAM soon. But what's the point of these two papers? Why? How is it possible that these people were able to optimize stuff and quite easily optimize stuff to be so much better? I want to think that there might be many factors, but the basic factor here is the intuition about what is possible. If we have a cluster of 128 nodes doing computation of this Twitter dataset, and one more information, this dataset was 3 gigabytes in size. The one that took Spark 1,700 seconds to compute. So if we see this cluster calculating data on 3 gigabytes of nodes, then it means that there's something wrong, and we have an option to optimize. What if this cluster works on 10 gigabytes, 10 terabytes of data? Can we know if there's something obviously wrong? Well, if we have intuition about what servers are there, what hardware is used there, and what this hardware is capable of, we can even from the start say that there's something wrong and there's probably some headroom to optimize stuff. So first is the intuition, and I would like to go to the last part of the presentation when I will show you some experiments using Java code to see how we can use the hardware best way, so that actually you can see the differences in proper usage of hardware and in improper usage of hardware. And it's in Java, so it's not like you need C or assembly to exploit all those things. It's even from the JVM it's possible. But first I want to do a quick refresher on how the processor looks like, how it works. Do you guys know what NUMA is? Non-uniform memory architecture. Okay, thanks. Some usual suspects, but now one more. Okay, so this is from Martin Thompson's blog. I found was the most informative diagram. You can have a lot of stuff or moving stuff in such a system. I will concentrate only a few things. So you have cores, and you see that there are two processors here in one system. What does it mean? What does it change in the architecture? We have cores. The cores have the register, so it's the data that is most close to it. It has several levels of caches. L1 and 2 caches are usually private to a core, and they are inclusive. This means that if something is in L2, in L1, then it will be placed in L2. L3 is usually a victim cache, so it contains all data that was thrown out of L1 and L2. And there is a memory, obviously, we need to get data from. The performance of modern disks are great, and this is topic for complete whole presentation. I will concentrate on data from RAM. We have memory controllers, and as you can see, with 2 sockets, we have RAM connected to some of them. So not every processor will have direct access to given memory. But if you program for this architecture, you see one continuous block of memory. You never have option to decide, at least in Java, where the data is placed. So does it impact the performance? Obviously, you need, if you have core running on socket 1 and you want to get the data from socket 2, you need to go through the interconnect. And the interconnect here is QPI. It's called Quick Path Interface, used by Intel. The intermarketing guys decided that it's not fast enough, so the new version is called Ultra Path Interconnect. Obviously, it's faster than Quick Path, right? But AMD went further, and they had hypertransport. Now it's called Infinity Fabric. So if there's too much watching Marvel, then probably this one is. And this setup creates what's called two NUMA domains. NUMA stands for non-unified memory access, and it means just that it depends how the memory access, its speed and throughput depends on when the data is placed. So it's non-uniform. This is something more interesting thing. It's an AMD EPIC processor for data centers. The CCX is core complex. There are 4 cores there. And as you can see, the connections are much more interesting. You might say it's not as clean as Intel, not as elegant, but that's the price of going adding much more cores. Let's go faster. This is, I always wanted to see it on the big screen. This is AMD processor with 96 logical cores, 48 physical cores. You can get it on Amazon for cheap. And they just released it a few months ago, so it was a very nice present for me. Let's run some tests and see how this architecture can impact our Java code. So this is the test setup. We have core number 0, and it will create a variable in some RAM place that is close to it, and we'll have all other cores trying to change this variable, and the core number 0 will change it back. So this will be a kind of ping-ponging, and depending, this is, well, it's a kind of real-life scenario. If you have something like Netty with event loop, or any system when there's signaling between threads, this is how the layout of data and threads will impact your code. Because all they do is send data somewhere and signal other threads, right? I use JMH. Is there someone that, do you know JMH framework, Java Micro Benchmark Harness? Okay, that's better, very nice. Like 1% of people. So think of it about like a JUnit for benchmarking, and some library that will allow me to control the memory layout. So this is first test. It's a setup. So like with JUnit, you will have setup and a test method. What I do here is to allocate a buffer on some NUMA node, and I ask the kernel to run this given thread on some other NUMA node. And here what I do is make this ping-ponging. So there are 2 benchmarks, 2 threads that run them, and what they do is, can I show it? What they do is change the variable from 0 to 1, and the other will wait until it's 1 and will change it back to 0. So what we measure here is how long does it take. So this is these are the results. Depending on where we put the data and where we put the threads, it can be as fast as 200 nanoseconds. And if the layout of the data is not optimal, it can be 650 nanoseconds. So just by placing cores and data correctly, we can make this signaling 3 times faster. This graph shows how in a little different way. We have a core number 0 that will send data and ping-pong it through other cores, and we can see actually when we go out of the socket, It's the most expensive one. And when we go out of the silicon die to a different core on the same socket, this is for Intel, so it's more consistent. There's less differences between the cores. So that's latency. There's one more thing, which is throughput. And when we have data, when we correctly place data into RAM, and we need to process it using our core. So the question is, having some modern architecture, how fast can we do it? Is this what's the throughput here? What we can do, is it half a gigabyte? Let's do some voting. Who says that it's about half a gigabyte per second? Maybe it's 2 gigabytes per second. Okay, maybe about 20 gigabytes per second. Maybe 100 gigabytes per second. Okay, so most of you are sleeping, okay? So obviously it depends, but the correct answer here is C for one core, which means that we can run at about the speed of 16, 18 gigabytes per second. This is the test code. It just goes through byte buffer, reading longs as fast as it can, and the result is that on AMD processor, here we have three NUMA nodes, so there are only 3 different distinct memory controllers. When we read data, it's about 18 gigabytes per second. If you read data on all the cores, you can have over 100 gigabytes per second. So if you have a data set of like 4 gigabytes and it takes tens of minutes to analyze it, then probably there's something wrong, or you have very dense scientific computations there. So if you think this is not fast enough, think about stuff like NVIDIA graphic cards, or the newest AMD cards can have up to 1 terabyte of memory bandwidth per second. Okay, you can see there are two bars here for every NUMA node. The lower one is when we do random access. So this 18 gigabytes goes to 400 megabytes per second when we do random access. And what's interesting here is that whatever the setup of NUMA nodes and data is, if we do streaming read, we get roughly the same performance, because processor is really good at prefetching stuff. But if we go to use random reads, first we go to 400 megabytes per second. Then if the data is placed incorrectly, we can go to as low as 200 megabytes per second. So this is the difference here between streaming, reading, and random access, as you can see, is great. Okay, we have 5 minutes. So quick tour through branch prediction. We have this 18 gigabytes per second. Why can't we process that fast if we have linear reading? I have an example with reading 400 megabytes of data. I will not make a quiz here, but let's say it's 100 million of integers in Java, and we read through them, and we want to execute a kind of query like see how many integers there are greater or lower than some value. This is scenario, for example, you have a data of how many users brought some stuff in your app, and you want to calculate how many of them bought anything. So it was larger than 0. So we stream through 400 megabytes of data. It should be about 20 milliseconds if we calculate from this here. Well, it isn't. It depends on branch prediction. So we have this very simple loop. We go through a byte buffer reading ints, and if the int in this case is smaller than some set value, we increment the counter. So there's almost no work here, just to go to this memory. So we should be streaming at 80 gigabytes per second, but that's not the case. Depending on branch predictor, we can do it in 43 milliseconds or 500 milliseconds. So here the selectivity means how often we match the predicate, which means that if selectivity is 10%, so 10% of the time our branch predictor was wrong, because it predicts usually based on some small history, and for 50% it's just random. Branch predictor cannot do any work here. So difference is again more than 10 times. There are techniques that can avoid this, and there's a white paper by by Leslie Lamport from 70s or 80s that described the technique to avoid this. At that time, probably something like integer was a vector register. It was very large. They described a set of computations that can be done on a value instead of conditional. So this example, when we have less than, we can replace with some set of instructions that will allow us to compute the correct result. Actually, the set of instructions is a set of masks, ands, or, and negations. And guess what? How faster or slower this? Actually, there's a lot of instructions here. How much faster or slower it is compared to just plain if. As you can see, it's slower than if in case the branch predictor was always right, but it's faster than the if condition, even if the 5%, there was 5% of the times the branch predictor was wrong. We're already faster than this, and using vector instructions and packing this data, we can, the fastest I was able to do, the code is on GitHub, maybe you can look at it and make it faster, was 11 milliseconds using techniques from this paper. So removing ifs can give you about 50 times improvements. It's not always a good idea. Here, this is from GitHub. There's a Doom version that is branchless. It uses no branches. It is compiled with compiler that will just issue more instructions. The problem is that it renders frame every 7 hours. So it requires somewhat increased patience. So that's the conclusion. What I wanted you to get from this is that you can wear two hats, 10 times developer and 0.1 times developer. The 0.1, you might think he has easy, he can just say, I'm not doing anything, just not implement this, does not do that. It's not that simple. But on the other hand, the 10 times developer, it's also not that simple, right? It's the crucial part is to know when we can, actually, when we have headroom to optimize. And in order to do that, we need to have at least the intuition, and then the tools to do this. So I started with intuition. The tools, I guess you can go and explore for yourself. These two approaches are not exclusives. Thank you.